Our next speaker is Dr. Kaiyu Guan. He is a Blue Waters professor and the founding director of Agroecosystem Sustainability Center at the University of Illinois, Urbana-Champaign. Dr. Guan is also the chief scientist for the NASA ACRES program. He got his PhD at Princeton University and was a postdoc fellow at Stanford University before he joined University of Illinois in 2016. His research group uses computational models, satellite data, fieldwork, and artificial intelligence to address how environment and human practices affect crop productivity, water resource availability, and ecosystem functioning. Guan's group aims to increase our society's resilience and adaptability to maintain sustainability of ecosystem services, food security, and water resources. In addition, Dr. Guan has published over 150 papers in leading scientific journals. I'll hand it off to you.
Yeah, hello, friends and colleagues, and it's really great to come back to talk and provide some of the updates. I use the title as thoughts on improving MRTN tool and then developing some of the new tools about P and K. And this is an effort that has been ongoing for a couple of years, and we were very lucky to get funding from NREC, from NIFA, and some fundings from National Science Foundation. This is a truly collaborative effort. As you may know, that I have been working with Emerson since my day one at Illinois, and has gained a lot of his help, and now he's helping my students. And at the same time, he has been working with Andrew, especially in the PK work. And then more recently with our newly joined faculty, John Jones, that start to look at more nitrogen. And then I have been working with Bing for a couple of years. Some farmers really has been working together, Dan Schiffer, John Pike. And then we also have some social scientists helping us to better understand how tools can be better used. And then so I'm gonna go into today's talk covering these aspects. So primarily these are two aspects. One is I want to show some of the MRTN tool. This is a classic, widely used tool, but also there's some thoughts, a lot of thoughts, I would say, what's the next step? And then so we're gonna kind of show some of the underlying thoughts about that, and going through a couple of scenarios. And then we're also gonna talk about some of the new efforts that we have been start to work on, especially related to PK. This is primarily the effort with Andrew Magnot's team, and then so we will touch on that. We will start with this classic graph. This is a classic graph that showing the x-axis showing the nitrogen rate, and then the y-axis is the crop yield. And then, just thinking about the x-axis at this moment is the rate and not the overall supply, just thinking about the rate. So from 0 to X amount of rate. 0 means you're applying no fertilizer in the field, X means X amount. And the y-axis refers to the crop yield. And this is a curve that we primarily rely on to underline the MRTN tool. And then so as you imagine that as you increase the rate from 0 to be certain amounts, you continue increase, crop yield are gonna increase continuously until you reach to a plateau. This is very widely understood. There's a couple of variables that I really want to identify. The first one is we call the Y0, and this is basically the yield you can achieve when you don't apply any fertilizer. And then the next one is basically the maximum amount of yield you can achieve by applying more fertilizer when you reach to the plateau. And then so this is we call Y1. And then when we achieve that Y1, for the first time, the minimum amount of rate that you achieve of Y1, we call it X1. So that's the rate that we believe is based on this particular framework of nitrogen response, yield response to nitrogen rate. That's kind of the maximum rate, the sort of ideal rate that we can hit. Now understand, this is the first part of the whole framework, because you have to plug this framework with the economics. Particularly, you need to integrate the price of the corn yield as well as the cost of the fertilizer. Potentially other aspects, but the MRTN tool currently developed by Emerson and others primarily consider these factors. So you will see this is kind of the classic MRTN tool that Emerson has been shown multiple times. On the left side, the top one is essentially a curve of what we just see. It's the yield and nitrogen yield response to nitrogen fertilizer rate. But then on the bottom part is where you add the economics. You add the economics of fertilizer rate, price, as well as the price for corn yield. And then you bundle these then together, you can find the maximum rate. So we're not gonna kind of look into the economics today because I think that part is relatively straightforward if you have the top right figure figured out. Because the price of corn and fertilizer pretty much is changing with the market, but it's sort of given. So the primary thing we're gonna focus today is really on the right top figure, which is this graph. So gonna revisit this, I'm gonna keep talking about this, so make sure we remember this. There's a couple of points that I mentioned, Y0, Y1, and X1. So these are the three primary things that I'm gonna talk about. The reality is we are doing these trials over many years, over 2 decades, many decades actually, through the trials. And then when we look at all the data, we find the data is not as clean as this curve. As a matter of fact, this is from the real data. This is from the real data that we have. So these are the data set that we collected over Emerson and the IFCA, and then our collaborators collected over the many couple of years that funded from different sources, but primarily funded by NREC, and then we've done these trials across the state. So when you look at this, the major question is, what's really going on? What's really going on about these curves? So if we fit anything, if we just say, okay, we're only gonna fit one line for the southern Illinois, for the central Illinois, for the northern Illinois, how much confidence do we have? Because it's a very complicated problem. I wouldn't say messy, because when you see the data, you feel its messiness apparently. But as scientists, as researchers, our goal is to really see, can we make sense out of this apparent messiness, and then start to make sense what really drives the underlying variabilities. So again, remind everybody, I'm gonna look at this graph, but I try to explain the variability. And today, I don't gonna provide a lot of data. I provide the conceptual diagrams. And this conceptual diagram is really the food for thought that I want everyone start to think, start to get some sense, like what we're gonna actually do next. So to start with, this particular nitrogen curve, I'm gonna call that nitrogen yield response. That particular curve that related to these 3 numbers, Y0, Y1, X1, gonna actually link with soil weather management. Obvious. Soil, particularly if you start to thinking about we grow the soil, our state soil in the north, in the west, in the central, in the south, they have a pretty dramatic gradients, which differ in SOC, in the sandy fraction, the rate, pH values. But also we talk about weather. The weather pattern is very different. The weather pattern not only different from the geography gradient, from south, north, west, but also it's different from year to year. We still can remember some year we have very floody year, some year we have very dry year. Even though we generally have enough rainfall, but temperature vary quite extensively for pre-growing season, for on the growing season. Last but not least, management practice. We start to get into more corn soybean rotation system. The rotation matters, whether you adopt cover crop or tillage practice. A couple of professors already mentioned they matter. Last but not least, fertilizer application. Timing, whether you use inhibitor or not, what's the type, what's the depths. These are all matter. So all of them, how we kind of kick into this particular nitrogen yield response curve. So we're gonna start with the first one. So this is a conceptual diagram. So I always need to make a comparison. So in able to make a comparison, I have the default case. And this default case, for the convenience, just imagine this particular default case is a particular farm in central Illinois, like in Champaign. Okay, so I'm not comparing with any other farms. Just for the particular talk, for the sake of this talk, I want to just say the default one I want you to compare with is the farm in central Illinois, in Champaign, let's put it this way. So this black curve in this graph refers to that particular default case. Now the red or the orange line refers to all the rest the same for that particular field, but they just slightly have a higher SOC, soil organic carbon. So what's gonna happen? Situation gonna happen in the following ways. First, if we look at the Y0, which is when you apply no fertilizer, you just have the soil provide a little more SOC, and then you can generally envisioning that soil actually basically is more fertile. They can mineralize more available nitrogen. And then so the zero rate yield will increase a little bit. At the same time, we also imagine increased SOC overall will also help increase the overall crop yield at the maximum rate. And then that rate primarily is because SOC is usually correlated with other better soil physical properties and other aspects that actually leads to increased yield a little bit. But another aspect that we want to say is that X1 rate will potentially move to a lower rate. And this is also obvious because the better SOC usually means that soil can do more job by itself by providing soil mineralization. And then this actually can be counted in as potentially reduce the rate you apply. So this is for SOC. Once you're familiar with this particular mental or concept, mental game, let's look at the next one will be easier. So we're gonna look at the next one. The next one gonna look at the drainage, tile drainage. So what we are looking at, the tile drainage is, the default case is in central Illinois, a Champaign field, but let's assume it's not tiled. So most of the fields in Champaign tiled, but we have some fields not tiled. And then we compare with the field, we assume that field is the same, but we just put some tile drainage infrastructure underneath. So what this usually happens is in the Champaign, in central Illinois situation, usually this means that the field will become more, water can actually get less water inundation situations. We're gonna have more oxygen in the soil, and then crop will usually grow better. And this is the major rationale why we use tile drainage. That basically means the Y0, if you add the tile in our system, we will increase Y0, the yield when you have no fertilizer, but also increase the Y1, the maximum yield rate you can achieve. At the same time, we acknowledge when you add tiles, Y1 increased because crop can grow better, so usually that means you need more fertilizer. But at the same time, there's a little more leaching happening if you have the tile. So you expect combine these factors together, you're gonna increase the fertilizer rate to achieve that maximum yield. So X1 gonna increase a little bit. So this is the situation when you compare a typical field in Champaign County with tile versus, without tile versus with tile. Now we're gonna talk about weather. We still remember 2012, it's a very big drought. So we're gonna look at a typical field, typical yield, black, which is normal yield, in most normal yield. And then the red one gonna be a drought yield, like 2012. So what this drought yield gonna lead to? We're gonna have, because generally they're gonna hit the yield no matter what, you apply fertilizer or not. So you're gonna reduce Y0, you're gonna reduce Y1, but because you also reduce Y1, you generally create less needs for nitrogen. You actually also reduce X1. So in other words, if you do have a crystal ball, you can imagine like this coming summer is actually gonna be very dry. So either you put a fertilizer in, either you put infrastructure of irrigation. Some of you may not have that, but most farmers in Illinois don't have that. But one possibility is, one thing is that the drought gonna hit, and then you probably don't need to put so much fertilizer. But that's based on the assumption that we have a crystal ball seeing the future. In most cases, seasonal or level weather forecast is still not very trustworthy. Now we get into the rate, fertilizer rate or fertilizer timing. And this particular one, again, the black one refers to a central Illinois Champaign County, and then the red one refers to we apply So the black one refers to we apply fertilizer in the springtime. The scenario, the red one refers to apply in the fall. So actually, this is an interesting situation because what we expect is Y0 doesn't really change much. So that's basically the situation like you don't apply fertilizer, then timing doesn't matter. But then for the Y0, for Y1, the maximum rate, we do believe they can achieve similarly. It's actually proven by many years of data by Emerson. But we do expect to see if you apply different season, fall compared with spring, because fall you apply earlier, you expect it during that winter time and springtime you may leach a little more. And then also it's very weather dependent. If you have a very warm winter, very flushy spring, you're probably gonna lose much more, the fertilizer you already applied. But then if your winter is cold, you have a pretty dry springtime, it probably have much less difference. But we do find from the data set that difference in the X1 is meaningful, statistically meaningful. Now, side dressing. So we compare with a field only apply fertilizer in the spring versus the scenario is we start to put in the side dressing. What's gonna happen? The primary thing that's gonna happen we find is the Y0 is not really changing much. The X1 doesn't change much, but the rate gonna actually shift a little bit. So in other words, the side dressing, which potentially may increase the nitrogen use efficiency at some situations, will reduce nitrogen rate overall. However, this is very weather dependent. So I get into a lot of deep discussion with Emerson and Johnson, and it's basically at what situation this side dressing make most sense. And then so usually what side dressing does nowadays for most farmers here in our state is we apply most in the spring, but then we start to apply in around V5, V6 stage. We usually don't apply further. At V5, V6 stage, it's between the springtime and the V5, V6 stage that during that period of time, if you get a lot of rainfall flush out, probably provide a supplement side dressing would be very beneficial. And those are usually indicating you actually can gain the benefits. But then if it's not really flushed out much, putting the side dressing sometimes does not really help yield. And then so this is have some also evidence, very rich empirical evidence to help us show all of that. Now, the rotation pattern. So we just choose the very simple rotation pattern. We are not even talking about complicated cover crop or pennycress addition, but we just look at the simple one. The simple one refers to the default one is corn soybean rotation. The scenario one refers to continuous corn. So this is actually you're gonna expect that is if you grow continuous corn compared with corn soybean rotation, you're actually gonna lose yield by doing continuous corn because the corn soybean rotation has its benefits of enriching the soil through the soybean. And then also there's the maximum yield gonna have some difference. We generally see corn soybean rotation can generate better yield over time and slightly lower amount of rate. So with all of that, I will stop here because I showed a couple of representative examples in a conceptual way, in a very conceptual way. What I want to get, what I want to inform and then actually stimulate the conversation and thought process is really to help you think what really drives these apparent messiness in the data. These are some of the very well formulated hypotheses to explain that. And then just imagine, come back to the framework. We know that soil gonna matter, weather gonna matter, management practice gonna matter. And then can we bundle all of them together with, continuous long-term support of the field work, field trials, and then potentially deploy more on-farm trials, and then integrate this with this framework, but also use models to start to really making sense of our data. So I don't gonna talk about model today because I think a lot of people have the suspicion that if you don't have really the experiments or empirical data, we will not believe models. And that's very, very important. I believe I agree with you. And this is why we do need long-term efforts to continue our cross-state effort and long-term effort for doing these trials. This is very important. And these well-defined experiments are going to help us to do the following things. They're going to help us to inform the scientific evidence, answer agronomic questions and science questions. And then on-farm data and long-term trials actually going to help us to significantly advance our understanding and to provide the data that helps us to understand the patterns that I just showed. I also have this belief is if on-farm trials, especially done by farmers, we can make it very easy to implement. And then they would happy to do that. I hope we can make it easy enough that they're willing to do that, they're happy to do that. But these type of data, if we properly integrate it with some of the sensing technology, some of the modeling technology, we may be able to provide very field-specific guidance to you. And then that's a really sincere kind of aspiration that we have. Now, we're going to talk a little bit about model. Some of you who know me, we are primarily doing the modeling work. We're primarily doing the remote sensing and modeling work. But what we believe is model has to be built on the experimental data set. And then we have to first make sure a model really can be validated and reproduce the patterns. But what we're going to actually validate with, it's going to be the empirical data. So what I believe is the model does provide abilities to assess all these scenarios that I just showed. The model can provide that scenario because in the model we can easily say, okay, increase fertilizer, reduce fertilizer, or increase temperature, reduce temperature. But all of these patterns or the embedded relationship revealed by the model needs to be first reproduce what we observe in the real world, which is the experiments. So this step needs to be done first, and then once we gain the confidence of the modeling, we can reproduce what has been observed, especially from these relationships. Then we can start to imagine, can we use models to integrate with particular on-farm trial data set and actually improve field level MRTN. I mean field level. I truly have this aspiration. I know that people have been dreaming about doing this for 2 decades. I was involved as a research intern, research scientist very briefly before I joined U of I. I was a research scientist with Climate Corp building their nitrogen advisor. And I know it did not go anywhere. And I also closely observe a lot of other nitrogen tools like AdaptN and others. I also feel they have a lot of challenges. This is why we know that there's not really very good tools out there. But then if we want to have an aspiration, if we want to paint an exciting time or the roadmap, how we actually move into the future, I do believe there's going to be an integration. It's the integration that we have the long-term trials, long-term stable support to do continuous trials across the state that has that representativeness. But also we want to start to see whether we could work with farmers to develop very easy implemented on-farm trials. And then these kind of useful data set integrating with proper modeling efforts, we potentially can have a way to really get to the field level. MRTN. So this is the high level kind of roadmap thinking, and then I think represent our stuff. So I want to see how much time I have. So I probably don't have much time, but I think I will wrap up the P very quickly. The P work is our ongoing effort, which is primarily based on the soil phosphorus rate, soil phosphorus concentration in the soil versus the relative yield. So, one of the major efforts Professor Andrew Magnot's team are working on is really try to come up with this with the cross-state effort from their long-term kind of efforts, and then thanks to NREC's support for that. Now, what we have been working on is working with Andrew's team, use their data, and it's keep coming, but then we use their data, try to refine this particular relationship. And then what we believe is when this relationship integrates with farmers' soil test, we can actually have a very good confidence about what's the rate of P we actually need to apply at these particular locations. And then this is, again, a long-term effort, and Andrew will talk more this afternoon about his PK work. But we do have a prototype effort to build the tools. This is a very conceptual one because at this moment we still divided Illinois into 3 parts for the PK tool. but I think the idea is really get some idea of how you actually conceptualize these tools, and then use that as feedback. We want to hear the feedback from the farmers, which we are doing this research with some of the NSF support, but we also interested in continue these efforts to ultimately build the tools. And then this option should allow farmers to input their soil test data such that you can get to very field-specific information that is relevant to your field. And that's the hope. So with that, I don't have time to demo these tools in a deep detail, but I will send a link to you all. But then I think this is the link you can click in. But then we continue working with Andrew's team. We have a very preliminary tool that want to gather inputs, but want to continue developing this for both MRTN and PK tool. And then we start to work more with, continue work with Andrew's team, continue work with Emerson, but we're also very excited to work with John. And then we do believe some of these thoughts represent our long-term effort of trying to work with farmers and trying to bring the best science together to come up with tools that benefit our state. Thank you.
Thank you, Dr. Guan. Are there any questions? Do we have time for questions, Julie? I think we do.
Yeah, I'm going to get them on.
Morning. I have a question.
Oh, please, yeah.
So I'm not an expert in modeling, but how do you deal with possible interactions between the factors that you mentioned, like soil factors, weather?
This is exactly the power of having the models. So in other words, if you do the trial experiments, you only have certain mutations to do that in the real field. So what we envision is you still do these mutations in the real field, but then what we could is use these data set to constrain and validate the model. But then once you have the model that you actually trust their response, you actually can go to simulate all sorts of the interactions. And then this is I did not expand too much on the modeling side because I presented before for a couple of times about modeling, but that's the power of having a model.